copies of TIFR which I have. Yeah. So my talk for today is on this topic of Fokker-Planck feedback control framework for optimal personalized therapies in colon cancer-induced angiogenesis. But before even starting the talk or the details, technical details of the talk, this talk is dedicated in the loving memory of my advisor and my sir, Professor Vasudeva Murthy, who was not only just a supervisor to me, but he was also like a father figure. He really guided me through the entire journey of my PhD, as well as other aspects of life. Okay, I always had his smile, his support. Whenever I felt down, I could look upon him and like feel very supported. And he was the one who actually inspired me to do research, which actually is motivated by a lot of practical day-to-day problems. For example, my PhD thesis on optical flow was motivated by issues with tracking cloud motion, which might help farmers in proper harvest or timely harvesting. So this talk and my entire work during my career has been dealing with problems which arise in practice in the day-to-day life. So my heartfelt condolences to his entire family, and I really thank you, sir, for inspiring me, and I really miss you. So to acknowledge this work, this is a joint work with Shubhropal from the Department of Mathematics and Zuipan from the College of Nursing and Health Innovation, both from the University of Texas at Arlington. The work of Paul and Roy was funded by the NCI-NIH award, and the work of Zuipan was funded by the NIH award stated here. And the reference for this talk is this paper. So colon cancer, which is actually the third leading cause of cancer deaths in USA, it actually begins in the large intestine, which is known as the colon, and which is also the final part of the digestive tract. Now, even the colon cancer can affect or usually affects the older adults, but it has been seen that it can also happen to people of any age. And the way it begins is it starts off as small non-cancerous clumps of cells, which are known as polyps. They actually form inside the colon. So that's kind of the middle figure here. And some of these polyps, they actually kind of grow into colon cancers, like full-fledged tumors, all the colon cancers. That's actually the progression from a polyp in stage 0 to stage 4 cancer. Now, what happens is when the polyp starts its formation, they are usually very small and they produce very few symptoms. And that's the reason colon cancer gets diagnosed at a very late stage. Okay. So angiogenesis, which is a process by which new blood vessels grow, they allow the delivery of oxygen nutrients to the body's tissues. This process is very much important or required for the growth and development, as well as for healing wounds. But on a negative side, once a cancer or a tumor grows, angiogenesis also helps in the growth of such tumors, because tumors are essentially tissues. So growth factors which help in the cell growth, differentiation, survival, inflammation, and tissue repairs, they're actually proteins. Okay. Yeah, this is so. Some of the there are several growth factors, and these are known as the tumor angiogenic factors that have been like associated with regulating angiogenesis in colon cancer. For example, one of them is the VEGF, the vascular endothelial growth factor. And in recent years, angiogenesis has actually become a very potential biomarker for detecting cancer, in fact, colon cancer. And subsequently, it's very important to control the angiogenesis mechanism to stop the spread of cancer. So this implies we need to develop efficient anti-angiogenic drugs. Now, some challenges in clinical cancer research. So for developing efficient drugs, so it is essential to understand several pharmaceutical concepts called such as the physiological effects, the pharmacodynamics and kinetics, maximum tolerable dosages, the shrinkage pattern of tumors, then the therapeutic intervention windows. So all these factors are quite crucial, and there are a lot more. So these are quite crucial in understanding the cancer mechanism as well as developing effective treatments. But to understand these mechanisms, a large number of clinical studies are often required, which is very, very expensive. And then another major clinical challenge is actually to obtain an effective treatment strategy for either one patient or for a group of patients with similar cancer characteristics. So because we have different groups of patients with different cancer characteristics, testing therapies or different kind of therapies during clinical trials is quite a cumbersome process, very expensive. And it's just even expensive to test one therapy and like get it FDA approved. And it has been observed that combination therapies are like actually more beneficial in treatment of cancers in comparison to single therapy. But these are from limited clinical studies. And it's, as I said, it's very expensive to test even one therapy. So combination therapies, they incur their own challenges. So for these clinical issues, mathematical and computational methods, they actually are a very efficient and effective way for assessing treatments. So one such class of mathematical and computational frameworks for analyzing the dynamics of cancer and then testing the effects of treatments is known as quantitative systems pharmacology, abbreviated as QSP. So QSP models help us understand the biological processes and identify biomarkers like angiogenesis, and they then predict treatment outcomes, and simultaneously also understand or help us understand what is the mechanism of drug resistance. Okay, so they're actually the primary tools to test the impact of drug parameters and biological variances on drug efficacies and safety. Now, the QSP models, they're represented by a set of differential equations, could be ordinary differential equations or partial differential equations. And these differential equations describe the dynamics of the cancer mechanism and their interaction with various drugs. Now, there have been several QSP models which have been developed for for cancer angiogenesis, but in almost like most of these models, the QSP models or the equations they consider are deterministic in nature, and they are unable to capture the randomness present in the usual or traditional cancer dynamics. For example, randomness could be present due to the mechanism of proliferation or random proliferation of cancer cells. Okay. Okay. So we start off with a QSP model for angiogenesis. And this QSP model was formulated by the authors in Souvik and Kovacs in 2019. And this QSP model describes the dynamics of vasculature volume and the interplay between tumor and vasculature volumes. Now, the dynamics of the tumor angiogenic factors, okay, is also described through this model. So in essence, This QSP model consists of a set of 3 differential equations whose model variables are V, the total tumor volume, capital B, the vasculature volume in the tumor, and capital T, the concentration of tumor angiogenic factors. So this is the governing system of ODs, which describe the QSP model for angiogenesis. Now note, in this model, we have additional some terms containing U1, U2, and U3, which actually represent drugs or dosages of various combination therapies, which we'll be determining later. And there are some other parameters or coefficients in this model, okay? And we represent those parameters as theta. These are kind of specific to the patient, and we need to determine them given the patient data. So we represent this unknown parameter vector, which is specific to the patient, as theta. Okay. So to stabilize and to properly scale the QSP model for implementation using numerical algorithms, we non-dimensionalize the OD system using these transformations, and then we obtained a similar looking transformed but non-dimensionless OD system, which now will be used for the mathematical frameworks. So what we kind of want to do here is, as I mentioned, that like most of the models for colon cancer, the QSP models for colon cancer are deterministic. We want to extend this model to stochastic models to incorporate the randomness in the cancer dynamics. So we kind of add the diffusion terms. Sigma 1, sigma 2, and sigma 3 are the diffusion coefficients. And DW1, DW2, and DW3, they are the one-dimensional Wiener processes. Okay. And with a compact notation, you can write the stochastic differential equation. Well, there's a misprint. There's the dt shouldn't be in the denominator. It should be to the right-hand side. So we have this specific stochastic differential equation, which is an extension of the original deterministic QSP model. So here dw in this compact notation represents the vector of the three-dimensional Wiener processes, and the bold sigma is the dispersion matrix. Okay. So analyzing or trying to come up with a mathematical framework using stochastic differential equations is a bit more like technically involved. So what we do is we kind of lift the stochastic differential equation or ordinary differential equation to a partial differential equation through the characterization of the probability density function corresponding to the random variable capital X. So if we consider that small f is the probability density function associated with the stochastic OD model vector variable capital X, then the stochastic differential equation, which we saw in the previous slide, is equivalent to the dynamics of this PDF or the evolution of this PDF modeled through the following Fokker-Planck equation. So here f of x comma t is actually the probability that capital X is equals to the vector small x at time t. And we know that the Fokker-Planck equation can be given in the flux form. And we consider the unknown vector theta and the drug dosages the non-dimensionalized drug dosages U bar I in the following admissible sets UAD and VAD. These sets are contain a few constants, which are MI, which represents the feasible biological ranges of the parameters. DI is the maximum tolerable dose for the drugs, and omega is the one-dimensional subdomain in the ith direction. And for restricting the Fokker-Planck equation to a bounded domain, we choose a non-reflecting boundary conditions or the no-flux boundary conditions. And we also have the conditions of positivity and conservativeness for the Fokker-Planck equation. So the goal of this work is to devise a Fokker-Planck optimization framework for obtaining optimal therapies. So prior work with the Fokker-Planck optimization framework, this framework has been used or successfully applied to various E2 processes, subdiffusion processes, piecewise deterministic processes, with applications related to pedestrian motion, game theory, collective motion, and these are some of the references. But to the best of our knowledge, this is actually the first work on Fokker-Planck optimization framework in context of colon cancer. So we now devise a Fokker-Planck algorithm for obtaining optimal therapies. So this is a three-step process. Okay. So the first step is we estimate the patient-specific unknown parameter vector theta, given the values of the PDF of capital X at specific time instance. So we denote these PDFs as Fi star of X. And for this purpose, we solve a finite dimensional optimization problem for obtaining the theta star. Now, once we get the theta star from the data F star, and we then try to determine the subset of the optimal parameter set theta star, which is kind of sensitive with respect to the tumor volume V. To do this, we'll use a global uncertainty and sensitivity analysis using the Latin hypercube sampling partial rank correlation coefficient method, abbreviated as LHS-PRCCI. So once we can identify the sensitive parameters, which kind of control the tumor volume, this will be used to formulate or to kind of determine which kind of drugs or which type of drugs can be used for controlling or treating the cancer, and the number of different types of drugs to be used. So this kind of gives you the combination. And then once we can ascertain the types of drugs that can be used, we will then formulate the optimal therapies using us by solving a second Fokker-Planck optimization problem for the UIs. Note here, we kind of minimize of the functional J2 over the set of UIs for which their associated coefficients alpha is a non-zero, which means those UIs are kind of like present in the model, which means we can exclude some of the drugs or we can include the other drugs. So we just minimize the functional over the drugs which we include. Okay. So we now move on to the theory of the Fokker-Planck optimization problem. So the solution of the Fokker-Planck equation, given a H1 initial condition, we have a non-negative unique solution in this space, and the solution of the Fokker-Planck is also conservative. We also have the following L2 stability result for the solution of the Fokker-Planck system, where the stability coefficients kind of depend on the drift function, which is kind of the right-hand side of the original deterministic OD, which includes the unknown parameter set theta and the drug dosages. And these are some other stability results corresponding to the solution of the Fokker-Planck equation. And we finally state the most important result of, or most important theoretical result of this work, which is the existence of minimizer of both the optimization problems, one for the parameter estimation and one for the optimal therapies. And the result is that if you start off with a non-zero, like a H1 initial condition for the Fokker-Planck equation, then we actually have minimizers theta star and nu star, which minimize the two functions J1 and J2 in their respective admissible sets, which means our minimization problem has a solution. The uniqueness of such solutions are kind of not easy to prove. They are like, they can be proved, but under very certain restrictive conditions, which are not biologically feasible. And in fact, the non-uniqueness of minimizers kind of help in giving us like different options for parameter ranges, as well as like different treatment options. So in hindsight, non-uniqueness might be, or potential non-uniqueness might be a good thing for such a setup. So once we have the theoretical results on this optimization problems, both the problems, we then derive the necessary optimality system, which in both the cases results in a set of three equations: the forward Fokker-Planck, the adjoint Fokker-Planck, and the optimality condition. Now we come to the numerical implementation of the Fokker-Planck and its adjoint. So to solve the Fokker-Planck equation numerically, we need to like use a scheme which can result in the numerical solution of the Fokker-Planck to be positive and conservative, because those are the theoretical properties of the solution of the Fokker-Planck. And we also want second order convergence. So we use a time splitting Douglas-Gunn scheme for the time discretization, and this is a kind of a three-step process. And for the spatial discretization, we use the second order Chang-Cooper scheme. So we have the scheme on the screen. So this is the three, as I mentioned, the three-step process. So starting with the known discretized function f at the time tm, we obtain at the final step, the third step, the discretized function f at time tm plus 1. Okay. So that's the Douglas-Gunn scheme for the time discretization, and for the spatial discretization, we use the Chang-Cooper scheme, which exploits the flux form of the Fokker-Planck equation and then approximates the flux script f using this expressions given on your screen. And this representation of the flux function results in the conservativeness and the positivity of the solutions of the Fokker-Planck equation, which is the kind of the result which we have shown here, that the combined DG3-CC scheme is positive under the CFL like condition given on your screen, and this condition depends also on the unknown parameters, the right hand side of the deterministic OD, and of course the drug dosages. And now we define the discrete L1 norm as this. So we have the following conservative property for the numerical solution, and then we have this following stability result in the discrete stability result in the L1 norm. And then we have the following results show the truncation error of the DG3-CC scheme is of order del t square plus 8 square under the CFL-like condition. And finally, we prove the L1 convergence of the DG3-CC scheme, which is also convergent with an error of order delta t square plus h square. So it's a second order convergent scheme for solving the Fokker-Planck equation. And for solving the adjoint equation, we use the standard finite difference schemes for approximating the derivatives. And for finally solving the optimization problem, we use the projected nonlinear conjugate gradient scheme, for which is kind of a modification of the linear or the traditional conjugate gradient scheme for solving optimization problems. So we now move on to the sensitivity analysis using the LHS-PRCCI method. So I don't have time to describe this entire method, but essentially in this method, we kind of, once we obtain the unknown parameters, which is a vector, for each parameter, we kind of specify a PDF, and that PDF will be corresponding to a V-bull distribution. And for each such parameter, we kind of like draw samples using Latin hypercube sampling to obtain a data set of m samples times the number of parameters, in this case, which is 6. And this is called the LHS matrix. And using this LHS matrix, we perform the PRCC, the partial rank correlation coefficient method, to kind of rank the parameters in their order of sensitivity. And parameters with large PRCC values and corresponding small values, they are actually quite sensitive. Okay, and we can also rank the parameters based on their PRCC values. So this is kind of a summary of the LHS PRCC method. Now we move on to the final section of this talk, which is the results. So we consider two type of data sets. One is to test the method or to mathematically, like to test the concept of this Fokker-Planck optimization framework. We first use a synthetic data measurements by solving the original OD in the time interval t equals to 0, 4 with number of data points 10 and 20, and with the corresponding non-dimensional parameters set theta. And from here we obtain the synthetic data measurements. So we have either 10 measurements or 20 measurements. And the second data set which we use is the real data set from these two papers, where they have measured the tumor volume and the corresponding measurements for B and T for like a C38 colon cancer or colon adenocarcinoma, which was transplanted or which was transplanted subcutaneously inside the mice, and the measurements were done using a small animal MRI. So the numerical setup, we choose our Fokker-Planck domain omega as 0,6 whole cube, and we discretize using 51 points in each direction. The final time t is chosen to be 4, and the maximum number of time steps is chosen to be 50. The patient data we have already described in the previous slide. We have those discrete data points, either 10 or 20 for the synthetic data set, and for the real data set also we have 10 points. But for our Fokker-Planck setup, we need to come up with PDFs of the data set. So for each data point, we assign a PDF around the data point described by a normal distribution with the mean value as the data point value and the variance is 0.05. And then we perform a 4D interpolation to obtain the data function f star. Now for determining the values of the dispersion coefficient, we analyze the data given in Scissorsic corresponding to the measurement of V in 10 mice on these corresponding days. We first compute the mean for the measurement of V for each of the corresponding days. And then we make an assumption that the standard deviation is given in this form. And we saw that with the values of Ra, M, and epsilon, this function kind of very well fits the given data set. And then we choose the corresponding sigma i's as this, which is non-negative. In fact, it's positive. So our Fokker-Planck is still a parabolic Fokker-Planck equation. Now, the first part of the numerical results, which is the parameter estimation process. The first row shows the plots for V, B, and T, the Monte Carlo plots, and we have the blue line as the mean of the Monte Carlo plots. And the second row kind of shows the mean within the blue, and the red curve is kind of the curve obtained using the parameters we obtain using the optimization framework. We then plug it into the OD model, and we then get the red curve. And so we see kind of that for the data with 10, like if you have 10 data points, then there is a bit of difference between the measured values of B, B, and T and the estimated values coming through the parameter estimation process. When we increase the number of samples from 10 to 20, we have a very nice or better fit. And then we perform a sensitivity analysis. So the obtained optimal parameter set for n equals to 10 and for n equals to 20 are given here. And we compute the p-value and the PRCC values. So we note that the C, which is the day of the tumor, and gamma, which is the tumor angiogenic factor coefficient, they have the least p-values or the greatest PRCC values, which means they are the most sensitive parameters. And so we want to use a combination drug that can control the effects of C and gamma. So what we do is we consider an anti-angiogenic inhibitor called bevacizumab and a chemotherapy drug called capecitabine that directly affects T and V. So this is kind of now the third step of the three-step optimal therapy process. So we now start off with the values of the non-dimensional model variables V bar, B bar, and T bar at the final non-dimensionless time T for T equals to 4, which corresponds to the parameter estimation step. And this is the time when we know that there is colon cancer. So our target is to use the optimal combination therapy to bring down the levels of V bar, B bar, and T bar to 111. That represents the cancer-free stage. So we do this with a dosage administration for a period of T belongs to 0, 1.4, which corresponds to the actual time of tau equals to 14 days. That's the actual time, not the non-dimensionless time, but the actual time. And this is actually also the time period corresponding to the standard combination treatment cycle with bevacizumab and any chemotherapy drug for colon cancer. So for this optimal combination therapy optimization problem, we consider the data function FD, or not the data, but the target data function, I should say, the target PDF to be a Gaussian centered about 111 at time T equals to 1.4. And we have the figures on the screen. So the first row shows the red curve shows the plot for, or the mean plot of V, B, and T if there is no treatment, which kind of shows there is an increase. And then if we administer the treatment, then we can kind of decrease it to the desired levels. And the second row shows the, well, it's not V and B, it's the drug dosages U1 and U2 for the capecitabine and the bevacizumab. And we kind of see the leftmost drug is the chemotherapy drug, which needs to be administered first as a huge amount, and then the profile decreases. And simultaneously, the anti-angiogenic drug kind of starts off with a low dose concentration, and then the profile increases or the dosage increases. We do the similar thing for the real data set. We do a parameter estimation, and we see the plots. The blue one is the measured data set, and the red one is the generated data set using our Fokker-Planck model with the obtained optimal parameters. We again do a sensitivity analysis, and we find again that the same C and gamma are still the sensitive parameters. So we still use the same combination therapy, the bevacizumab and the capecitabine. Okay, yeah. And this is the first row, again, kind of tells us that with the combination therapies, we can kind of decrease the tumor profile or reduce the colon cancer, even with this real data set. And we observe the same behavior for the drug dosages. That means the chemotherapy drug kind of starts off with a higher dosage and then kind of decreases. And the reverse is noted for the anti-angiogenic drug. Okay. So as an inference, so from the two aforementioned experiments, so we kind of see that the combination therapy with bevacizumab and capecitabine provides an optimal treatment regime. And this is actually consistent with the previous experimental studies, where it has been demonstrated that combination therapies work far more better than single therapies. But it has also been noted that bevacizumab in combination with other chemotherapy drugs might elevate like secondary risk factors. So it is very important to administer low dosages of both these drugs. Now, from the numerical results we see, it was not quite visible probably with the color bars, but the maximum dosage of capecitabine required was approximately 900 milligram per meter square per day. And for bevacizumab, it was 0.55 milligram per kg per day. But this is significantly lower than the current acceptable practice of administering 1250 milligram per meter square per day dosage of capecitabine and 10 milligram per kg repeated over a 2-week period. So this framework kind of shows us that constant administering of the drug for a couple of weeks will actually be a more effective strategy in administering lower dosages, and hence the side effects would be far more lower. Okay, and so we'll have a lower toxicity level and will prevent secondary risk factors. And this is also the same observation with the results, the experimental results presented in that paper from where the data was taken. Okay, and as I mentioned, like that the concentration of capecitabine decreases over time, whereas the anti-angiogenic drug increases over time. So this actually suggests that it might be feasible to use the bevacizumab as the primary treatment in combination. Okay, or once the colon cancer is controlled, then bevacizumab might be a better drug to use for treatment. Okay, we don't need to consider the chemotherapy drug at all. And chemotherapy drugs have been associated with high toxicity levels with like numerous secondary risk factors compared to anti-angiogenic drugs. So in hindsight, this framework kind of provides the very effective treatment regime. Okay. So to conclude, we have presented a new stochastic framework for obtaining personalized treatment strategies in colon cancer-induced angiogenesis. For doing this, we use a model or a QSP model, okay, governed by whose dynamics is given by the Fokker-Planck equation, and then the coefficients of this Fokker-Planck equation represents the unknown patient-specific parameters that we can estimate using the patient data, and this is done through a PD constraint optimization problem. We also presented robust discretization schemes for solving the parameter estimation problem, as well as the second problem for optimal combination therapies. which is based on the feedback from the sensitivity analysis of the parameters, and the numerical results with synthetic data and real data using experimental mice demonstrates that the optimal combination therapies for colon cancer-induced angiogenesis can actually be obtained using this framework in real time with high accuracy. These are some of the references, some clinical references, and thank you so much for your attention.